Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is black holes. And here to tell us all about them is our guest, Professor Ed Cackett. Ed, welcome to the program.
Thank you. Great to be with you.
Why don't we start out by having you tell our audience a little bit about yourself and what you do.
Yes, so my name's Ed Cackett. I'm a professor at Wayne State University and chair of the Department of Physics and Astronomy there. I've been at Wayne State for about 10 years. And my area of research is on black holes and neutron stars. So I'm very excited to talk to you about them today.
Yeah, I'm sure we'll hear a little bit more about that as we get into the program. Now, black holes are something that a lot of people are interested in, especially the younger kids. In my working with them, in my jobs at the Science Center in Cranbrook, the kids were always asking me about black holes. So let's start out with, what is a black hole?
So there's a little graphic to how to describe what black holes are. And to talk about black holes, you really have to talk about gravity. And the sort of our modern understanding of gravity really comes from Einstein and his theory called the theory of general relativity. And what Einstein told us was that any object that has a mass, so a star, a planet, a human, that bends the fabric of space and time. So we can think of it graphically like this, that space is this grid here of green lines. And then an object with mass, like in this case, the sun and the earth, causes a bend in space-time. The more massive the object, the bigger the dip you get in space. So you can also think about this as in terms of a trampoline. And if you put a bowling ball on a trampoline, that bowling ball will cause the trampoline to dip. So that's the sort of picture you should have in your mind when you think about what an object with mass does to space. So we can step this forward and say, okay, an object like the sun bends space a little bit. It's enough for the Earth and all the planets in our solar system to be forced to move around in orbit around the sun. But as you go more extreme, by more extreme I mean cramming that mass into a smaller amount of space, then the curvature of space becomes more extreme too. So there are types of stars called white dwarfs. These are dead stars. Our sun will become a white dwarf at its end of its life. It's about the size of the Earth, and that causes a much more significant dip in space. More extreme still, a neutron star. It's about 10 kilometers across, 10 kilometers in radius. And that, again, has a really deep dip, causes a really dense and steep curvature of space. You actually have to travel about almost half the speed of light to be able to escape from the surface of a neutron star. For comparison, to be able to escape from the surface of Earth, you have to travel about 7 miles per second, right? So the more extreme it gets, the higher the speed you have to be traveling to be able to escape that object's gravity. So then we come to a black hole. So what's a black hole? It's an object where space is curved so much that the velocity that you have to travel, the speed you have to travel to be able to escape the black hole is greater than the speed of light. Now, the speed of light is the ultimate speed limit in the universe. We don't know how you can't travel faster than the speed of light. So once you get too close to a black hole, you pass the region called the event horizon, then you can't escape. Even light can't escape. This is the sort of point of no return. So black holes are this extreme object where once you get too close, even light cannot escape from them.
The event horizon sounds like a place that you don't want to get too close to. Now, how do these black holes form?
So When stars are in their normal life, they are in balance essentially, right? So gravity is pulling all the material of the star in, but inside the star, we have nuclear fusion going on, and that's actually the powerhouse of what's powering the sun and powering all of the stars. And that's pushing outwards. So we have gravity pulling in and nuclear fusion pushing outwards. Those two forces balance, and a star nicely stays stable as an object like the sun. However, eventually the fuel inside a star can run out. And for the cases of the most massive objects, object stars that are about greater than about 20 times the mass of our sun, they go nuclear fusion all the way up to the element iron, and then they run out of fuel. You can no longer have nuclear fusion taking place. So now you're no longer in balance. Right? We had gravity pulling in and nuclear fusion pushing out, but if you turn off the nuclear fusion, all you have is gravity pulling in. And so you have a catastrophic collapse and then actually an explosion as stuff gets pushed back out again that we call a supernova. And there are different types of supernovae and ones that come from stars that are more than 20 times the mass of the sun will end up in such a catastrophic collapse, you end up with a black hole at the end. This is an example of what a supernova looks like, supernova remnant looks like. This is what we're seeing in this image is a supernova, the gas left over from a supernova that went off about 1,000 years ago in the year 1006. What we're seeing now is the outer layers of the star that have been traveling for 1,000 years outwards into space. And there's potentially a black hole left behind at the center. We don't know in this particular case. It's not been detected yet, but this sort of explosion, this sort of supernova can leave a black hole behind.
Now, I understand there's more than just one type of black hole. Can you explain that for our viewers, please?
Yes, so the black holes I've told you about so far are black holes that end up being what we call stellar mass black holes, a few times to a few tens of times the mass of our sun. But there are another type of black hole that have been found, and these are called supermassive black holes. So these are black holes that are supermassive. They are millions to billions of times the mass of our sun. And we see these in the center of almost every major galaxy in the universe. This is an example of a galaxy where there is a supermassive black hole at the center. This is called M87. This is an image taken by the Hubble Space Telescope. And the blurry yellow stuff you can see is actually the stars. This is an elliptical galaxy. But you should notice at the very, very center, it's extremely bright. And you can see a jet coming out. This is a jet of gas, plasma that's been blown away from a billion mass solar black hole at the very center of this object. And it's bright because there's material falling into that black hole.
Now, this plasma that we see coming out of the black hole, we say that light can't escape, but how is it that plasma can do this? Does it follow magnetic lines?
Yes, so you have, as long as you don't go past the event horizon, things can still escape. And this material around the black hole is definitely magnetized, and it actually, black holes can spin, and that can actually twist the magnetic field lines. And so this material then can get pushed out following the magnetic field lines that have been twisted up by the black hole. And that can lead to these incredible looking jets.
Interesting. Now, I know in the past we've developed methods to indirectly observe a black hole. What are those methods like?
Yes, so when we think about how might we detect that a black hole is actually there, you can say, well, we can do this because we know that black hole has gravity. And so even though light can't escape the black hole itself, we can actually see the presence of it there by the motions of things nearby the black hole. So we can take a look at our own galaxy, the Milky Way, and look at the center. And what you see here is a little animation showing you the motion of stars. It's these rainbow-colored things in this animation that have been observed around the center of the Milky Way over a period of around about 25 years. So there have been two teams, a team led by Andrea Ghez at UCLA and a team led by Reinhard Genzel at the Max Planck Institute for Extragalactic Physics in Germany. And those two teams have been monitoring the center of our galaxy, the Milky Way, for the last 25 years. And what they see is that these stars are orbiting around something, and something that's not emitting a significant amount of light. And what you can see, there's one star here that's highlighted in yellow, actually does a complete orbit. Right? And another star here, the one that was in green, I'll show you that again in just a second, actually gets so close to the black hole, it gets slingshotted back out again. Play that one last time. So if you watch this one here, Sirius 16, it's going to come in and get shot back out again. And so you can actually use the motions of these stars and actually apply Newton's laws of gravity to figure out what the mass of the object must be that causes this sort of orbital motion. And you can show that you need a 4 million solar mass black hole, so a black hole that's 4 million times the mass of our sun, sitting at the very center of the Milky Way. And this is work that won the 2020 Nobel Prize in Physics.
Very interesting indeed. We're going to take a quick break right now. For our viewers, if you have a question, please send us an email. The address you can find down at the bottom of your screen. And coming up next with Term of the Month is Stephen.
Thanks, Don. The term of the month is Dimorphos. Back in December of 2021, we talked about the NASA DART mission, which is designed to slam into an asteroid. DART, the Double Asteroid Redirection Test, is designed to hit Dimorphos, one of two asteroids that orbit each other. The other asteroid is called Didymos. The idea is to alter the orbit in a measurable way via a kinetic impact. The mass and speed of the DART mission spacecraft will be well known, the same for the asteroids. The math tells us what should happen. The impact is not expected to break Dimorphos or send it off flying. This is a technology test. Eventually, it should lead to Earth protection. We'll see if the asteroid Dimorphos changes its orbit as expected. By the time you see this episode, the impact event will have been over. It hit or it missed or whatever. That was September 26th. But this show was shot sooner, so we can't report it. Perhaps you could look it up. We'll all wait until 2026 when ESA's Hera mission visits the system for a close-up look. And that's Term of the Month, Dimorphos. Back to you, Don.
Thanks, Stephen, and welcome back. We're talking with Professor Ed Cackett from Wayne State University about black holes. Now, Ed, in the first part, we talked about an indirect method of seeing black holes, but I understand there's been some direct images made of black holes. Can you talk about that, please?
Yeah, so I think one of the most exciting developments in the last few years has actually been the first direct images of a black hole. In fact, two now, actually. So how was this done? This was done with a telescope called the Event Horizon Telescope, which is actually a series of radio telescopes that are around the globe from the South Pole to Hawaii and Chile and elsewhere, and they connect them all together so that they act like one Earth-sized radio telescope. And this allows them to then get extremely high spatial resolution, be able to view very small angles on the sky. To give you an idea, they can see, they can actually resolve about 1/1000th of a degree, which is about the same as having a donut on the moon. Okay, so
oh my!
how brilliant these telescopes actually are. And so this is what they found. You can see these images here. The thing that is black and looks like a hole is the black hole. And the orange stuff around it is the gas that's falling into the black hole. And the black hole is black because light that's traveling towards the black hole gets pulled in. And so we can't see any light that's from the black hole itself. This ring, actually the size of the hole in the center tells us about how massive the black hole is. So in the galaxy M87, the one I showed you the Hubble Space Telescope image of before, we're able to show that this black hole is 6.5 billion times the mass of our sun. And on the right is actually the black hole at the center of the Milky Way. It's called Sagittarius A star. And again, from the size of the hole at the center, they're able to again confirm that this black hole mass is 4 million times the mass of the sun.
So using this method, sort of interferometer with the radio telescopes that you were mentioning, they got one really big telescope to get these kinds of images. Now, are supermassive black holes important?
Yeah, so although at the moment we can only image directly those two supermassive black holes, it turns out from studies that every major galaxy in the universe seems to have a supermassive black hole. And that supermassive black hole actually has a really big impact on the galaxy and the material around it. So just to give you an example, a direct example of that, on the left here is an image of the center of a cluster of galaxies called the Perseus cluster. And there's a galaxy right at the very center here. And when you look at it in X-rays and radio, you get quite a different view than when you're looking at it in optical. So if we zoom into the center and look at in X-rays here on the right-hand side in blue, what you see is these sort of bubbles. And these bubbles are bubbles that have been blown in the hot gas that actually travels throughout all this cluster by the jets of the black hole. How do we know it's the jets of the black hole doing it? Well, when we look at radio waves, and you can see that in magenta in the bottom right here, you can actually see the shape of the jets of the black hole. And they fit exactly into the bubbles that we see in the X-rays. So what's happening here then, material is falling into the supermassive black hole. It's launching these jets out. These jets are actually bigger than the galaxy itself. And they're pushing material away from the galaxy. So the black hole is affecting the entire galaxy and even beyond the galaxy into the rest of the galaxy cluster.
Interesting. I hadn't really thought about that part of it before, so it's interesting to see how important the massive black holes really are. Now, I'd like to take some time here during the program to have you tell us a little bit about your own research.
Okay, so material falling into black holes has this big impact on the galaxy. And so we actually want to really try and understand how things fall into black holes. Now, when we look at most of these supermassive black holes, we cannot directly image them, but we have to use some other technique to try and figure out what's going on in these black holes. And so what we do is a technique called echo mapping. And I think a nice analogy is to think about standing in a cave or a large cavern shouting your name and listening to the echo. So if you shout, hello, you hear the echo back, you can actually figure out how big that cavern is. We know what the speed of sound is. And so by timing how long it takes the echo to get to us, we can then work back to figure out how big the cavern is. We do the same thing, rather than using echoes of sound, using echoes of light. And so we can actually see material light echoing off material around the black hole and coming to us. And by measuring those echoes, we can actually then figure out the size scale of the region around the black hole and figure out how material is falling into the black hole. So this is a technique called echo mapping or reverberation mapping, and it's been around for a number of years. And I think one of the most recent exciting things has been to do this at X-ray wavelengths. So this is a paper that I was closely involved in using NICA, which is a really interesting mission. It's an X-ray mission that sits on the outside of the International Space Station. It's this thing here in the white circle. It's about the size of a washing machine. As I said, it's strapped on the outside and it can move around and point at different X-ray objects in the sky. But we play this game of looking at the X-rays from this region around the black hole, and we can try and figure out the geometry of how stuff's falling into the black hole. And before our study, there were two competing ideas. One was that as this object evolves, the disk of gas moves in and out as it falls into the black hole. Another one is that the base of the jet moves up and down as things fall into the black hole. And we were actually able to show that it's the corona or the jet that's changing as things fall into the black hole by looking at these time lags and these echoes. And so this was a really exciting find that was published in Nature a couple of years ago.
Well, that's interesting. I had never thought about the rate at which material fell into the hole and how it would get closer and then recede. So that's some really good and new information for me. Ed, I want to thank you for taking the time out of your busy schedule to record this program so our viewers can learn a whole lot more about black holes. If you have any questions or just want to check out more stuff, which is a technical term, by the way, check out our website. The address is down at the bottom of your screen. And coming up to finish up the show, What's Up in the Night Sky with Stephen.
Thanks, Don. What's up in the night sky for October 2022? The moons, we start with a first quarter on the 2nd of October. We have a full moon on the 9th, the third quarter is on the 17th, and new moon is on the 25th. Now shown here on the 1st of October, a little bit before sunrise, we have Mercury in Virgo, which rises about an hour to a half an hour over the month before sunrise. Venus moves from Virgo to Libra over the month and rises about a half an hour at best before the sun. And at the end of the month, it sets near sunset. And that's because we have superior conjunction October 22nd. Venus is going to be tough to spot throughout the month of October. Now on the 22nd of October, this is 2-3 hours after sunset, we have Mars in Taurus, which rises 3 to 2.5 hours after sunset and is best at the beginning of the month. Uranus is in Aries and rises about an hour after sunset. Jupiter is in Pisces. It had opposition in September, so it's going to be up most of the night. Neptune is in Aquarius, but it's very near Jupiter, so it's also up most of the night. And then finally, Saturn we have in Capricornus, and it sets around midnight, and Pluto is in Sagittarius, but is best seen as soon as it is dark after sunset. This is the solar system, again on the 22nd of October. And that's when Venus has a superior conjunction. So if you make a line between Venus and the Sun and follow that line over to the other side to the Earth in the inset, then that's more or less a straight line, Venus, Sun, Earth. And that's how you get superior conjunction. Now, Venus isn't obliterated by the Sun necessarily. It might be above or below the Sun. The orbits are not in a flat plane exactly. And that's what's up in the night sky for October 2022. Now remember, we don't charge money for this show, but we may tax your brain.